Well, hello everyone. Welcome to our webinar this evening. Thanks for joining us. My name is Tim Cole. I'm the Clinical Affairs Manager for Heidelberg UK. I'm joined this evening by my colleague Emily. She's got the Academy name on her screen, but Emily's the head of our UK Academy team. And really, it's really with my great pleasure that I'm introducing to you this evening Professor Donald Hood. So Professor Hood is based in Columbia University in New York, and he's behind the Hood Visual Science Lab. And what he's going to be doing tonight is taking you through his wonderful interactive talk about the Hood Report. Now, if you're not familiar with this, what the Hood Report is, from our perspective in Heidelberg, is a report you can generate so long as you have the GMPE module. And what it does, it utilizes the posterior pole scan with the optic nerve head scan that we take with the GMPE module. So Don's going to go through how his report works and how to read this report. But as he goes along, he's going to stop a few times as we go through this. As I say, we're going to try and keep this as interactive as possible. But he wanted me to tell you all this evening that no question is too simple. So honestly, anything you can think of, please type it into the chat if you can. If you're new to the GoTo platform, you can do that from just the little question mark button in your GoTo toolbar. So just type away and fire your questions at us. What's going to happen is shortly Emily and I will vanish, but we'll be in the background collating all your questions, and then we'll pitch them to Don when he stops.
Thank you. Greetings, and thank you for inviting me to give this lecture. I'm going to tell you about an approach to understanding and diagnosing glaucomatous damage. The lecture has 5 parts, and I'm going to pause after 3 of these parts for questions. And actually, let me repeat what Tim said. It's not that not only is no question too simple, but no question is too dumb. Because if you think a question is dumb and you're embarrassed to ask, chances are it's the same question everyone else is embarrassed to ask. So simple, or if you consider it, dumb questions are welcome. So let me start, or let me also tell you that in case you fall asleep, which I hope doesn't happen, the parts 3 and 4, parts 1 and 2 are going to be background information that you need to understand 3 and 4. Part 3 and 4 are going to be the heart of this, where I'm going to tell you about the Heidelberg Hood report, and then I'm going to tell you how you can quickly, in most cases, understand and diagnose glaucomatous damage. So let's start with some real basic information. First, I think many of you will know much of this information. If you do, just use it as an opportunity to make sure we're using the same terminology. I'm going to start simply with a little review of retinal anatomy so that we use the same terms. So this is, oh, by the way, can you see my cursor? Tim?
Yes, we can, Don.
Oh, yes, Don, yeah.
It's big enough?
Yeah, it looks great.
Here, yeah. Okay,
great. All right. So this is an electron micrograph of a piece of a human retina about here. You can see the 3 layers of the cell bodies in the retina, the rods and cones, the bipolars, and then the ganglion cells, the star of the show today. Light comes in, of course, this way, absorbed by the outer segment, and then the electrochemical activity flows towards the brain, with the receptors synapsing on the bipolars, the bipolars synapsing on the dendrites of the ganglion cells, and then out via the axon of the ganglion cell. And you have about 1 million ganglion cells and 1 million optic nerve or axon fibers. All right, so receptors in the nuclear layer, and then the layers that are important to us today, the interplexiform layer, the ganglion cell layer, and the retinal nerve fiber layer, which contains the axons of the ganglion cells, as well as glial cells and blood vessels. Now, the second thing I want to remind you of is that glaucoma kills retinal ganglion cells and their axons. So this layer is affected, the ganglion cell layer is affected, and the retinal nerve fiber layer is affected. The second really important aspect of anatomy you need to know to understand glaucoma and the reports is how the axons, the retinal nerve fibers, the axons of the ganglion cells travel to the optic disc. So you probably have all seen schematics like this. You may have had that in books where you had to do reviews. It's meant to capture the following aspects. The ganglion cells on the nasal side or disc side of the fovea send their axons more or less straight in, but the ganglion cells on the opposite side, the temporal side, their axons during development arc around to avoid the fovea, and they bunch up here in the inferior quadrant. Now remember, this is a small part of the back of the eye. So you've got a lot of retina in other places sending, and a lot of ganglion cells sending their axons into the same region. So this region right here is a region that's particularly vulnerable to damage from glaucoma. I didn't draw all the axons in here, but the same thing is true up here in the superior quadrant, particularly vulnerable to glaucomatous damage. Now here's the key part. Glaucoma does its damage in and at the disc. So local damage here produces this characteristic arcuate pattern. Right? So when we're looking to diagnose glaucoma, we are looking for damage that's typically an arcuate-like pattern. Next ABC we have to review. As I think nearly everyone knows, there's no litmus test for glaucoma. There's no single test you can do to tell you that a patient has glaucoma. It's very common to define glaucoma as a progressive optic neuropathy, that is a disease of the optic nerve that progresses, that's characterized by a particular pattern of anatomical and behavioral changes. So let's pick apart this definition. By anatomical, we mean the fundus exam when you examine the disc, aided in some cases by photos, including maybe stereo photos. Photos are slowly being replaced. The exam is not being replaced, but the photos themselves in many cases are being replaced or at least augmented with OCT now. When it comes to behavioral change, we're talking about the visual field that is used pretty much around the world and that you're familiar with. Now, notice it says particular pattern. What is that pattern? Well, you probably guessed it. That pattern is an arcuate pattern that's characteristic of glaucoma. All right, then. So then the next is just a brief review of OCT, which stands, of course, for optical coherence tomography. It's a non-invasive measure of retinal anatomy. You can think of it as ultrasound with light. So just the way you can pick up a millimeter or two lump in the breast with ultrasound, because light has a shorter wavelength, you can actually pick up the difference in layers of the retina better than 10 microns. It is an incredible technology that has changed the way optometrists and ophthalmologists go about their work. So here's a single line scan, or sometimes called a B scan, through the back of my eye. You're looking at about this much of the back of my eye. This, I always point out, this is not me. This is post-mortem histology. It is human tissue. But if it were my tissue, it would sit right up here. So let's blow this up so we can compare this, which is a light microscope image of a stained human retina, to a very alive retina. So I just want to remind you of the layers of interest here again. Let's look at the retinal nerve fiber layer. Here it is on OCT. Here it is on the light microscope. Here it is on the electron microscope, right? It's made up of axons from ganglion cells. So these are little ganglion cells. This is it. I drew in one axon. You can see the retinal nerve fiber layer is very thin close to the fovea because there are very few ganglion cells. As you move towards the optic nerve, this layer gets thicker and thicker. I just drew one in here too. All right, retinal ganglion cell plus inner plexiform layer. That's these layers here and this layer here. And those are the layers. So if I were to ask you, if I were to tell you that glaucoma kills retinal ganglion cells and their axons, and I ask you to label on here which layers are affected, right? I'm assuming that you would say, well, let's see, this would be the ganglion cells in here, this would be their axons, this must be the retinal ganglion cell plus inner plexiform layer, and this band here is the retinal nerve fiber layer. You see it getting thicker and thicker because there are more and more axons being recruited. Okay, so the answer is what layers are affected? It's the retinal ganglion cell and inner plexiform layer and retinal nerve fiber layer. All right, so that's the ABCs. Now, slightly more complicated, but absolutely key to understanding the report is what should I look for in an OCT glaucoma report. So I'm going to tell you what you should look for no matter what company's report you're going to look at. But of course, I'm going to tell you about the Heidelberg Hood report in a moment. All right, so here is a report that we had been using in the lab since, 2002 or so, 2012 or so rather, and maybe a little before. And in 2014, a student and I, Ali Raza, wrote up this report because this is what we were using with the specialists we were working with. And it's a one-page report to help clinicians quickly diagnose and also understand, and I'll come back to understand at the end of the talk, glaucomatous damage. All right, so let's look at the elements. So first of all, this particular report is based on 2 cube scans, each with a number of B scans. So 1 cube scan is centered on the disc, 1 on the fovea. I'll show you in a moment, you don't need 2 separate ones, but this is the way this was done, right? And as we say in the article, this is more than just a report. This is really the embodiment of a process. And the process has various principles behind it, or today I'll call them rules, that you should always use or look for. So rule number 1 is a high quality circle scan is essential to the way I'm going to teach you to look for glaucomatous damage. So in this particular case, for this patient, here is the high quality circle scan. Actually, there are 2 ways you can get a circle scan. You can actually get it by averaging, or you can actually derive it from this. The average one is typically going to have better resolution. All right, now, when you look at this, you're asking 2 questions. The first has to do with segmentation and image quality. So by segmentation, I mean the computer has put these green lines on the borders of the retinal nerve fiber layer. Did it do a good job? You want to know that before you proceed. A. And also, what about the image quality? Now, here's something that may or may not surprise you based on how you've learned to read this. A lot of time is spent telling people they have to look at whatever the image quality statistic is on the report. In the 10 years or more I've been working with this, I have never, ever looked at a manufacturer's assessment of image quality. There's no need to. Look at the image itself to see if you can trust it. The second reason for looking at this is you're looking to see if it looks normal. This looks pretty good. That's suspicious, however. All right. Rule number 2, you want to make sure that the report has thickness maps for both the ganglion cell layer and the retinal nerve fiber layer. So let me define that. So here, from the cube scan around the disc, you're going to get the retinal nerve fiber layer thickness. And so here is a pseudo color map of retinal nerve fiber layer thickness. Red is very thick. Dark blue is very thin. From the cube scan of the disc centered on the fovea, you're going to get both retinal nerve fiber layer thickness as well as ganglion cell thickness. And so here's ganglion cell thickness. Thick is red, thin is blue. Rule 2B, right? If possible, you want to go beyond looking at simply the thickness maps, because if the reports allow you to look at ganglion cell and retinal nerve fiber layer deviation or probability maps, sometimes they're called deviations, sometimes probability maps. If the report has that's often a better way to see damage than a simple thickness map. So what do I mean by a probability map? Well, here's how the probability maps are determined. The software in the machine takes the thickness map and point by point compares the thickness of this patient to the values of norms. And so the way you read this kind of a map is dark red is significant at the 0.1% or 0.001, say 0.1%. By the way, red would be 1%, yellow would be 5%, and then green's not significant, greater than 0.1%, greater than 10%. We're going to, now this is a key step, we're going to flip this along the horizontal meridian and present it in field view. And the reason we're going to flip it and present it in field view is we're going to add later to this visual field points to compare it to perimetry and visual fields. So I want to remind you, if this is confusing you, I want to remind you, if you're looking at this, and let's say you're looking at this arrow, on the back of your eye, it's upside down. So we're flipping this so we can compare it to visual fields that you're actually looking at. Okay, so in addition to the retinal nerve, in addition to the ganglion cell probability map, we have a retinal nerve fiber layer probability map. Again, it's in field view, and in this case, it's created from these two cube scan maps, field view. So again, red highly significant, green within normal limits. And so here you have the ganglion cell probability map, and here you have the retinal nerve fiber layer probability map. Rule number 3, you want to look for topographical agreement of glaucomatous damage within the report. Now, before I define what I mean by this, let me give you a landmark that's going to be important for us, and that's the macula. Now, macula, you'll find that anatomists versus clinicians, there are various different definitions in the literature for macula. By macula, I'm going to mean the region plus or minus 8 degrees from fixation. So let's go back to our fundus photo again. This is a circle with an 8-degree radius, right? This area in here is the macula. It's less than 2% of the retinal area, of all your retinal area. Because don't forget, you've got a lot of retinal area outside of this fundus photograph. Here is your ganglion cell thickness map. Notice how thick the ganglion cells, so this is very thick. That's thin in the center fovea, but it's thin outside this region too. So this region here in the macula is packed with ganglion cells, right? And you have this donut appearance because they've been pushed away during development and they group here. But look at all the ganglion cells. In fact, although this is less than 2% of the area, it has more than 30% of all your ganglion cells. This is the region that's absolutely essential if you want to recognize his faces, if you want to read, if you want to drive. Here is a B scan through this, and you can see the thick retinal ganglion cell placenta plexiform layer here. All right, so where is the macula on your circumpapillary plot? So you're probably already familiar with this thickness plot of the retinal nerve fiber layer around the disc. If not, I'll repeat in a moment where it comes from. But you're probably familiar with this thickness plot, right? It is plotted in what the original, the way it was done originally in the Zeiss machines, and it's often called a T-snit plot. And the reason it's called a T-snit plot is because it is plotted here, starting temporally, that's the T, going superior, that's the S, to nasal, that's the N, you get the picture, inferior temporal, T-snit plot. So nasal disc is here, temporal disc is here. What that does is it splits the macula in two, right? Which just makes it a little more difficult, I think, to understand the topography. And in fact, this doesn't even split it at halfway. It's asymmetrical because of the way the disc sits versus the fovea. We have been arguing for years, and now many of the reports have this option, that it should be plotted in end-stin, right? That is, it should be plotted as if it started in the nasal, went to superior, went to temporal, and back to inferior, back to nasal. Because then the center of this is the center of your visual field, is the center of your retina, where fixation and the fovea would be about here. All right, so the image here And this thickness plot, which this black line is the distance between these green lines, it's the thickness of the retinal nerve fiber layer. They should be in the end-stin, and that's what you're going to see in the Heidelberg report in a moment. So that's your macula right there. Okay, so remember, we're looking for, so let's go back to the rule number 3. We're looking for topographical agreement. So what do we mean by topographical agreement? So we're looking for damage that's typically an arcuate, like so, right? Everything here should agree with this, with the premise that it is an arcuate. So let's take an example. This region here is decreased. You can actually see a little dip here. This is all decreased here. That corresponds, because this is in field view, to this part of the disc. And this would be the part, or the arcuate, that'd be associated, the arcuates that'd be associated with that part of the disc. This black arrow is in the same location as this black arrow and as this black arrow. Okay, this damage here and here is here. So right away you look at this and you see that this looks like glaucoma. Everything is agreeing, and everything is agreeing that it's impinging on your macula. All right, so finally, rule number 4. If you want to compare visual fields, you want to use deviation maps from the visual field, not summary statistics. You don't want to compare your OCT to mean deviation or pattern deviation or glaucoma hemifield test. You will not get agreement as good as you'll get if you compare the deviation maps. So let me give you an illustration. This field here has what you would probably recognize as a nasal step. So we took these points and we colored them in here. Well, does that agree with everything else we're seeing? I mean, it's way out here. You know, the visual field is not even within what we're scanning here, right? Well, this is a good illustration that this is missing macular damage. Look at the macular damage here and here. Remember, this circle here is your macula. You can see this clear damage here and here and here. All right, what about the 24-2? Well, here are 24-2 points that are abnormal. If we put them on top here, so these little black marks are the location of the test points. Here's the abnormal region. You can see the topographical agreement. The 24-2 missed that. The 10-2 sees it, gets it, as does the OCT report. Now you might say, wait a minute. I've been taught that you'll see damage in OCT before visual field. Isn't it the case you have to lose ganglion cells before you see visual field loss? And the answer is no, no, no. That is just wrong. That's only right if you stick to mean deviation, pattern standard deviation, glaucoma hemifield test. And I don't have time to go into it, but if you look at these 2 recent papers of ours, you'll see, as the title indicates, the structure function agreement is better than commonly thought. If you're comparing abnormal parts, the agreement is remarkably good. Okay, third part, and after this part, we'll pause for questions. So I hope you've been asking your simple questions. So now let's talk about the Heidelberg Hood report. Okay, so there are 2 versions of this. There's a version available in the US, and there's a version available outside the US, in particular in the UK, where I think most of you folks are. These 2 versions are identical for the left half of it, right? The right half is different. The deviation maps or the probability maps haven't been approved yet in the US. They are on this report here. All right. So I'm going to tell you about this report because this one is very similar to what I just told you. There are no new principles, general principles anyway, just a couple minor differences. All right. So this report makes use of the Glaucoma Module Premium Edition. It doesn't use all the different aspects of it. In particular, it uses this cube scan that has 61 horizontal B scans. And it uses the circle scan, the smallest circle at the moment from the circle scan. All right. You may already be using this. This is actually one of my favorite stock printouts from Heidelberg. This is a retinal nerve fiber layer analysis of circle scans, right? Essentially, this is identical to this, except this is T-SNP and this is N-STIN, right? This is the retinal nerve fiber layer. You can see some damage there. And then this is your macula in the center because it's in N-STIN. If that's not clear, make sure you add a question to the chat. All right, this may help. I'm going to blow this up, right? So N-STIN means we're starting here and scanning in this direction, starting there. This is the temporal half of the disc, so it's this half here. And this whole half here corresponds to your visual field. It's about plus or minus 15 degrees plus the nasal step of the visual field. And then this part here is the macula. All right, back to this. So in addition to this circle scan analysis over here, we make use of the cube scan to get our thickness plots and our probability plots. So again, we're going to be looking at retinal nerve fiber layer thickness here. So this is a retinal nerve fiber layer thickness map, just like the one I was showing you, but notice it includes the disc and the fovea. And this is the ganglion cell layer. So here's the ganglion cell thickness map, right? And this is centered on, on the fovea. You can see the fovea here. Okay, and then this. So let's just go through. Let's review this report at the same time we review the rules. Rule number 1: you want a high quality circle scan. Well, the Spectralis produces a beautiful circle scan. Right, so here's the circle scan for this particular patient, right? You want to examine this to make sure that these segmentation lines, they're red and blue in this case, are not making mistakes. They look very good here. You want to see if there's damage. You can see local damage there, right? Rule number 2, I told you wanted ganglion cell and retinal nerve fiber thickness maps. The old reports used to just focus on retinal nerve fiber layer. That's why I'm emphasizing this. So there's your ganglion cell thickness map, right? Let's blow it up, right? That's the thickness map. The only thing that's a little different about this map in terms of the Spectralis is that dark red is not the thickest. Actually, white's the thickest. The scale is just the pseudo color is a little different. So they go to dark red is very thick, but white is even thicker. And dark blue is thin. This, remember, is superior retina, because this is in retinal view. We're going to get a probability map, we're going to flip it along the horizontal. So now this is inferior retina and upper visual field. We turn that into a probability map, and that's what this is here. So this is now inferior retina, upper visual field. And this is the ganglion cell probability map. Red is 1% significance, yellow is 5%, green's within normal limits. And then here is another difference that distinguishes Spectralis and Heidelberg reports from some of the competitors. They've chosen to also show the regions that are significantly thicker. So this violet here is at the 99% level, and the purple is at the 95% level. This, typically, you're going to ignore this. However, when you have epiretinal membranes and some aberrant problems with segmentation, sometimes this is everywhere, and then you have a problem. Okay, these points here are your 10-2 locations. All right, remember I said you want probability maps from your thickness maps. So this is the thickness for the retinal nerve fiber layer. Flipped into field view, turned into a probability map. So very much like what I showed you, and these are the 24-2 points, very much like I showed you for the report that we created in 2014. All right, finally, let's review the rule 4. If you want to compare visual fields, use deviation maps from 24-2 and 10-2, not summary statistics. So here's how this would work. If you circle these points here, you can see that this is part of an arcuate here. So there's an arcuate defect like this that's showing up better on the visual field here, but better on the OCT here. Again, notice that the visual field extends out beyond what you see in the scan. Here's the 10-2. We can circle those points. There they are. And again, here is your arcuate. You can see that these are in topographical agreement, meaning that this and this is part of the same arcuate. In some cases, this will be very local, and this will stop here, but that's the same defect. It's just showing up better in the ganglion cell in the temporal part and better here in the nasal part. This is what it would look like on the US version, if some of my colleagues are tuned in. And again, you could just make the same comparison. All right, so let me end this section with an example of the efficacy of this approach. So this patient is a 46-year-old woman who was referred by a neuro-ophthalmologist in in Connecticut. And before I tell you about her results, let me just tell you that this particular neuro-ophthalmologist occasionally sends us patients, and in virtually every single case, they are very difficult patients. And if we can, not difficult behaviorally, but difficult in terms of to understand what's going on. And if we can figure it out, it usually takes us considerable time and all our tools. In this particular case, it was very easy to understand what was going on. And I'll show you why in a moment. But for 5 years, this patient noted a gray smudge in her upper visual field of her right eye. So here it is. This is a defect that she was reporting, right? So the neuro-ophthalmologist did a 30-2 and an OCT report. This comes from him. He was worried. He wanted to know whether this was retina or optic nerve. He was leaning towards optic nerve, but this turned out. So this looked more optic nerve to him, but he thought it could be retina too. And it turned out this was normal. Everything looked normal to him. So he sent it to us as a puzzle. Well, it's not really a puzzle, is it? That is, those of you who are really used to this, you can see there's damage. Well, let me ask you, is there damage in the optic nerve? And if so, why? Give it a moment's thought. So do you think there's damage? Well, you might notice this. Let's blow it up. See this notch here? That's real. That's also occurring in the most vulnerable part of your disc. Remember, this is a T-SNP plot. All right, so we scanned this patient. You can see, here's the report. You're done, right? This is very clearly optic neuropathy, likely glaucoma, right? And there's an arcuate defect. There it is on the scan. There it is on the local thickness plot, on the end-stent plot, right, in the macula. So it's somewhere here. All these black arrows now, by the way, are in the same physical location. So this location corresponds to that, corresponds to that. You can see here that it's impinging on the macula, and there it is on the ganglion cell, and there it is on the thickness map. These 3 red arrows are all in the same location too, and they're topographically related via an arcuate to the black arrows. Everything should agree. All right, so again, rule number 4, let's compare the visual fields. Here's the person's visual fields. Let's circle these points. There it is. Good agreement. Here's the 10-2. There it is, almost perfect agreement. Right. For those of you who haven't thought about how 10-2s are related to 24-2s, if we take this and scale it so it's in the same scale as a 24-2, it would cover that little region right there. So that's why sometimes you can miss these on a 24-2. All right, let me pause for questions.
Thanks very much, John. So we got a real mix, to be honest. A lot of the really simple, basic questions.
Can you speak up?
Oh, sorry. Can you hear me okay? Is that better?
I don't know why you're a little dim. Okay.
Okay.
I can hear you okay, Tim.
Can you hear me okay?
Yeah, I can.
I'll try and shout as loud as I can, Don, if you can hear
Yeah,
me.
I can hear you, but okay. Somebody
Is it-
started mowing a lawn outside too, but anyway.
Oh, no. Okay, right. Well, as I was saying, a lot of these simple questions you've actually answered as you've gone along, Don, but I've made a list of some of the ones which you might be able to hopefully answer here. So the first one is the Hood report still useful with very high myopic eyes?
Ah, yes, that's not a dumb question. I thought we were going to get dumb questions. That's a very good question. We just published a paper 6 months ago or so, and the title gives it away. The title says OCT can be used in most eyes with high myopia. So the simple answer is yes, you can. You should read this paper because the paper is almost a how-to model method rather. The circle scan, the small circle sometimes gets messed up due to epiretinal membranes. But usually you can see the circle scan, and if you can't, you can go to a bigger circle, which comes with the machine at least. And typically you can make use of the ganglion cell because even if the retinal nerve fiber layer, because of the disc, is a little funny, the macular ganglion cell plot, is usually some distance away from your myopic changes that are most damaging. What you can't do is trust the methods and use these pie charts. But you'll see, I don't use the pie charts.
Yeah, that's great. Thank you.
Is that clear, Tim?
Yeah, that's very clear. Yeah. So another question, kind of along the same lines, really, is does the Hood report have an age cutoff? Do you think?
The simple answer is no, because again, I don't use these metrics that depend on age. With age, you could get generalized thinning, perhaps. But there's nothing unique to the report that would be affected by that. The simple answer is no. Simple answer is no.
Right. Okay. Another one. Do you see any value in the Hood report for other types of optic neuropathies?
Oh, yes, definitely. Yeah, definitely. So other type, so I think the two most common, I mean, you can correct me if I'm wrong, Tim. I think two of the most common, other than just artifacts, I think two of the most common optic neuropathies that are confused with glaucoma is ischemic optic neuropathy and superior segmental hyperplasia. We commonly see patients, especially ION, because it's more common, but also SSOH, that are being treated for glaucoma. And so, for example, a patient, you can often pick it up on here, although the best place to pick it up, of course, is on your fundus exam, right? But on here, the patients with ION often this will be flat, where this will be very healthy. When I see that pattern, seldom that's glaucoma. Typically, that is ION. And I think on my website, I have a lecture where I talk about diseases masquerading as glaucoma.
Right. Brilliant. Thanks, Don. Now, I think you did answer this quite emphatically, actually, but again, I'm going to ask you again anyway, just for you to kind of really clarify this, because I'll be honest, this is a question I get asked all the time, and my fellow academy friends when we're training. It's all about this sequence of destruction with glaucoma. So is the ganglion cell always the first thing to go with glaucoma?
I think it's like, so first of all, I think we have to keep in mind is glaucoma is a very slowly progressing disease, So if you remember your physiology, if you damage an axon, right, you're going to get retrograde degeneration back to the cell body in days, right? And then the cell bodies are going to disappear in weeks. That's classic neurophysiology, neuroanatomy, right? So presumably that's happening here too. That is, if you actually acutely raise pressure, let's say, and acutely killed the axon at the disc, the first thing that you're going to see is retinal nerve fiber layer change, and then you're going to see ganglion cell change. But that is happening over a time period. So a couple of cells are happening at a time, and your testing period is such that you're probably not going to see that unless you do some very fancy statistical analysis or tracking. So in terms of these reports, you can practically at least consider them happening simultaneously. Although underneath it, it's more complicated.
Okay, I think that's very clear. Well, what do you want to do, John? Do you want to carry on now, or do you want to get? Because I mean, questions are.
I think I probably should carry on so we stay within the time limit.
Great. Okay. Well, I'll vanish again, and I'll pop back when you're ready.
Okay. All right, so the next, I'm going to talk about a step-by-step method for identifying glaucomatous damage. So this is a very practical part, and then I'll take questions on this separately since it's so important. So this 4-step method I'm going to tell you about for detecting and understanding glaucomatous damage is really been fine-tuned recently based on a project I've been working on with my colleagues at Columbia. So Jeff Liebman and Gus Demores and our other colleagues at Columbia have been struggling with how we can formalize the definition for OCT, and we'll have these publications soon. I'm not going to go into our definition. I just want to give credit to my colleagues for having influenced how I'm about to teach this. So the first step is you're going to look at the retinal nerve fiber layer probability map, and you're going to ask, is there an arcuate-like abnormal region on this probability map that's associated with this part of the disc? Well, the short version is, are you seeing an arcuate damage? Do you see arcuate damage in terms of a red region, right, with the abnormal, right, on this retinal nerve fiber layer thickness map, and remind you it's in field view? The answer here is clearly no. There's no arcuate damage, right? Step number 2. Is the B scan consistent? So you blow up the B scan, and by consistent, I mean, does this look normal? Well, there's a little segmentation error, but that's not the patient's fault. But you look at this, that looks beautiful, right? So the answer is yes, it's consistent with a normal looking retinal nerve fiber layer probability map. You're done. You're done. This is not glaucoma. You can look at these other things to see if they agree, but don't get misled by any of that, including don't get misled by whatever's over here. If this is clean like this, and this looks good, you are done. This is not glaucoma. This is not optic neuropathy either. All right, let's take the other one. Let's suppose it's a clear yes. And so by yes, I mean we're seeing clear red here, and these are clear. You got 2 clear arcuates. You know, are they artifacts? You know, sometimes you can get artifacts that are due to vessel location or something. Well, step number 2, let's look at the scan. Is this consistent? Well, look at this. I hope you can see this. I think it's just big enough on the screen. Look at this. There's damage everywhere here. Damage here, damage there. So the answer is yes, this is consistent, right? Again, you're done. This is optic neuropathy. You want to do a fundus exam to make sure that you can rule out other diseases, right? But in this case, it was glaucoma. All right. Let's take a different example that might be a little more difficult for the reason I'll tell you. So you look at this again. This is a yes. You know, not clear what this is. It looks like it could be part of this, could not be. But anyway, clearly the answer to this question is yes. Now we look at the image. You know, to my trained eye, I think that's abnormal, but I'm not going to call that if I were you, you know, especially when you're starting out. I would say not sure at this point. But we've only used these 2 pieces, all right? So here's a really important part of this analysis. Step number 3 is there topographical correspondence between the abnormal region between an abnormal region on this, right, and an abnormal region up here? So are these part of the same arcuate defect, right? All right, so there's damage here, right? This is damage. That is right down here. Remember, this is right here. This is in field view. This would be here. So this abnormal region here, or this abnormal region here, we could have done it right here, is could produce arcuate damage anywhere inside this here. And you can see that's topographically agreeing. You put this on top of this, like here, you can see this is all part of the same defect. It just shows up a little better on ganglion cells here, a little better on retinal nerve fiber layer over there. So you are done. So I can't emphasize this enough, because this is a great way to avoid being confused by artifacts. This is optic neuropathy consistent with glaucoma, right? And here's the point. When you have clear abnormal regions on both the retinal nerve fiber layer and the ganglion cell probability maps that are topographically agreeing, meaning they're part of the same, arcuate region, right? You have optic neuropathy. Now you can look at the rest of this to see if it agrees, but again, this is, here's your answer. If this was an artifact, you wouldn't have this too. That's why I say it's a good way to distinguish real from artifactual. All right, so if you need a tutorial on how you relate regions of your retinal nerve fiber layer thickness map to regions on the probability maps, then here's a review article that you can take a look at your leisure. All right, now to help out, we're developing, and we'll publish probably within the next couple of months, I hope, a catalog to help you with this first step. So what do I mean by that? So we'll have examples of yes. So examples of yes, all of these red arrows are clear arcuates. If you see anything like this, I want you to say yes, because that's a clear arcuate. I'm not saying it's not an artifact. It might be an artifact, but it's a clear arcuate according to this method. All of these are clear no's. Remember, sometimes you're going to see blues which are significantly thicker, right? Sometimes you're going to see little tiny traces here along blood vessels. Right? And then you're going to have the ones that we can't put in here and can't put down there. We're going to try to make this as small as we can, but there's an overlap between the extremes of your subtle patients and controls that might be thinner than average, or let's say in the 5% thinness range. Right? So all of these where there isn't quite a clear arcuate, in clear red, would be uncertain. And as I said, we'll expand this and probably do a separate paper on it. All right, so now here's an example. What do you do about this? Is there an arcuate region on the probability map? And the answer is, well, I'm not certain if there is or not. Okay, so let's take a look at this. Well, this could be normal. Is that abnormal? I don't know. I mean, I honestly don't know, just looking at this, to tell you the truth. So that's uncertain. Now we get to number 3. Is there a topographical corresponding region? Well, that suggests that, but that could so easily, it's so little, that could, I'm not going to say anything other than uncertain, or suggestive, but uncertain. So we've got uncertain, 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 which means we need the last step. And the last step means take a look at these other sources of information. So this here, to me, looks like there's a little bit of a hint of an arcuate. So this is probably real, not artifactual, and suggests that this might be real, right? And so this region here, and this region here, and this region here, and this region here, that they're all the same region. So I'm not super confident that's going to happen to you, but I'm giving this a tentative yes. And if I was forced by you to say whether it's optic neuropathy consistent with glaucoma, I would say yes, but I would say let's follow this patient with a 10-2 and an OCT. All right, now having said that, at some point I'll do a separate recording for artifacts and advanced complicated issues, but 90% or more of your patients that are coming in are going to fall into one or two categories. They're going to be clear no's. Remember, this is just a little extra thick, probably because the vessel's there. Is the scan consistent? Yes, you're done. So 90% or more is going to fall into either that category. And again, by the way, we ignore this over here. Or it's going to fall into this category. Yes, Yes. Optic neuropathy consistent with glaucoma. All right. Tim, what do we have for questions?
Okay, so I'm intrigued to hear your answer to this myself, actually. A few people have asked this. Are the field points on the Hood report actually calibrated to the posterior pole image that we see, or are they estimations like a virtual projection over this data?
Yeah, they're the simple answer is they're just estimations, but you'll notice, let me go back here. You'll notice that these are morphed. You see,
Yeah.
That's not the way the 10-2 looks.
Yeah.
And that's because light falling here, that's the ganglion cell that's actually being stimulated, because the ganglion cells are pushed away from the fovea. So we take into consideration that morphing, the morphing of those points due to the fact that the ganglion cells are pushed aside. We don't adjust that for individual patients. That's based on something like only 6 or 7 post-mortem eyes published by Drasdo, Curcio, and colleagues, right? There's a fair amount of literature out there now, testing this that matches our own experience, that this is remarkably good in most patients. If you get extreme patients that have extreme dystophobia angles, then this could be off a little bit.
Yeah.
For quantitative work, that can throw you off occasionally. For clinical work, it doesn't. So, for example, if you had just a red spot here and just a little red here, and you had a whole bunch of points that were above the red spot, you're gonna say, well, that looks like I've got structure function agreement. But that usually doesn't happen. Usually the overlap's quite good.
Right.
Did I answer the question, by the way, Tim?
Yeah, you did. Yeah. Well, I've got my second question actually links to this one. And again, this is one that a few people have actually said as well. They're saying, what's the point in having the 24-2 on the Hood report? Because, a lot of the spots on the actual thickness information. Is there a reason that you wanted to keep that 24-2 there?
Yeah, I think that again, that's a very good question, and that gets to a deeper question is what should you be doing in terms of which field you should be using. But the answer is, first of all, many people are still only doing 24-2s. A mistake, by the way, but that's a separate issue. That's A. And B, once you understand the topographical relationship, remember, we were able to diagnose structure function agreement based on a nasal step. So if these points are abnormal here, if this was a real eye, if this was an eye and the field, for whatever reason, was subtle, it was just abnormal here, well, that's structure function agreement.
Oh, I see. Okay. Yeah.
So we have a separate paper on that where we're using a model, and eventually this will find its way into a report, but we're using a model to trace out the predicted region here so that the user will be able to put a marker here and see the whole region that's associated with it, even the region that's outside the OCT.
Mm-hmm. Mm-hmm. And actually track the axon back. Is that what you mean from that place outside the picture?
Yeah. I mean, what this is predicting is that your retinal nerve fiber layer is going to, if you could get this region, would be abnormal, right? Yeah. But it may not even show up abnormal because at that point the layer is so thick it's hard to see. So this region here, actually, your visual field is going to be better off at picking up damage here than your OCT is going to be.
Right. Yeah. Okay. Great. That's answered that one. How are we doing for time here, Don? Because I'm just conscious of the clock there. Shall I leave the last few questions for the after part 5 then?
I think you can ask another question or two here. I think we're doing pretty well, aren't we? Yeah, I think we're doing pretty.
We're just coming up. It's about 4 minutes left of our allotted time actually, so we better.
We are. I'm sorry. I'm off. Yes, no, leave. Let's go.
Okay. Right, I'll vanish again. I'll pop back in a second. Okay.
Okay. Bye-bye. All right. So in the remaining time here, I want to focus now on the understanding part. So we've been dealing with the diagnosing part. Let's do the understanding part. All right, so let's take this eye here. It's a clear yes. It's a clear yes. We know this patient has glaucoma. We know it's fairly advanced. What else can we learn? So let's blow up this image here, right? This is the center 8 degrees. Here is plus or minus 15 degrees plus the nasal step, right? All right, now, looking at this, what do I know? I know there are deep defects here in both the upper and lower hemiretinas, right? And it includes the upper and lower macula. So here's the macula. So that you're going to have deep defects in both the 24-2 and the 10-2. I know that. The other is you're going to have preservation here in the very central part of the visual field, right? And I can tell you right now, if this were my eye and you were my doctor, I would say, see this, please preserve that for me, because that's why I can see my grandchildren. That's why I can drive. That's why I can read. I don't care about any of these pie charts. This is what I want you to save. Okay? So let's just take a look at that. We've got this region here. So here's the visual field. Here's the 24-2. Let's look at this abnormal region. You can see the agreement. You can see the agreement up here. I want you to notice, see how deep that defect is, minus 27 and so on, minus 23. Here's the 10-2, right? We put this on here. Again, see how deep the defect is. Okay, same thing for the lower visual field. I'll just put these up in the interest of time. Again, you can see how deep the defect is in these regions, right? And you can see the preserved visual field. You can follow progression with this report. Here's this patient in 2015. That's what we've been looking at. Here's this patient 4 years later. If you flip between the two of these and put a cursor any place, you'll see there's a very, very subtle progression. So whoever was the doctor here is doing a pretty good job of preserving that region. I mean, 4 years, that's not much change, right? And in fact, if we blow it up here, you can see that this is the recent one. That's the early one. You can see there's a slight thinning here compared to here, partially due to age, partially due to progression. But not a bad job. You're preserving this person's vision. Compare it to this. So here's 2016, 2020 almost. So 4 years. Can you see the change everywhere? More importantly, you can look at the image itself. This is 2016. Here is the most recent. Look at the loss of tissue, and it's marching towards fixation. For those of you who use the GPA report, this is not going to be good news, this particular picture, because this has not been changing at all, but yet that's been going on. All right, then finally, just 2 minutes on advanced glaucoma. The common wisdom is you cannot use OCT for advanced glaucoma. The answer is that is just not true. So the rule of thumb is if your global thickness is less than 40 or 50 microns, then you're in the noise level. Well, that much is true. You can't use these metrics, right? In fact, the fact is OCT is useful for many eyes with advanced glaucoma, but you're going to have to ignore the metrics such as global or regional thickness, right? And instead, you're going to have to look at the circle scan image as well as the ganglia cells and retinal nerve fibrillary maps. So if you look at this patient here, so first of all, let me give you a rule of thumb. You're going to ask me, is that true with all advanced glaucoma? And I'm going to say no. Here's the rule of thumb. If there is a region on the 24-2 or 10-2 visual field better than about -8, even a point or two, there's a good chance there'll be tissue remaining that you can follow. So let's take this example here. This eye here, here's your 10-2, right? If we blow this up, there it is. That's the tissue remaining. That's what you want to retain. If this was your eye, this is what you want to retain, right? So forget the metrics. Right? Here's the visual field. We can flip this around, and this region of the visual field corresponds to this. If you keep this, you'll keep that. If you keep this, you'll keep that. And we've been following patients now using this method for 4 to 5 years. Just forget this over here. Okay, so that's basically it, Tim. So do we have time for any questions? Up to you.
Thank you so much, John. I mean, to be completely honest, we've still got really high numbers. Everyone's still hung on. So I want to thank everyone for sticking right the way through. I'm sorry we have gone over a couple of minutes, but again, that's absolutely fine, John. We did stop a couple of times in the middle, so the timing's actually perfect. I do have some more questions if you're happy to just hang on a little bit more.
I can stay here as long as you want.
Okay. I mean, to be completely honest, we have had a complete ton of questions here, but as you've been going along, as I said in the previous gaps, you've answered a lot of these as you've been speaking, actually, just naturally. So again, it's hard to do this virtually, isn't it? And understand that you're doing that. But if there was a sea of nodding heads, you would have seen those.
Oh, good. Yeah, I really need that, but this is good. Okay.
I can virtually see that. But I do have a couple of questions for you still. So
Okay.
one is actually about ethnicity. Do you think that ethnicity affects those posterior pole images that you see with the, because obviously the normative data doesn't stretch to every ethnic group, does it? So, I mean, is that something that we can consider when we're looking at the Hood report?
Yeah, that's a good question. Heidelberg is very good about having different normative groups, and other data is still being collected. There are differences if you look at, and there are papers on this. If you look at the global statistics, there's some differences. We've seen some too, but if you're actually looking at the report, it's small change. Long as you don't take these things seriously here, and I don't use them at all, and you're looking for this kind of you're using the rules I made, the minor differences among ethnic groups is not going to affect the use of this report.
Right.
Of course, it's always nice to have norms as close as possible, but I'd be very surprised. So what would it do? It would do, if you had an eye like this, maybe it could be more extreme in one group and it could be a little less extreme in another group, depending on the average thickness. But that's going to be a small change compared to just looking at agreement here.
Yeah. Now, I have noticed you've been putting a box over those pie charts, normative pie charts in the bottom left. Do you think if we did a Hood report 2.0, we'd take those out? Would you like? And then we'd maybe make the other images bigger? What would you like to see?
You're going to get me in trouble with some of your colleagues.
I'm going to get in trouble as well.
The answer is, yeah, I'd love to replace those with a fundus photo.
Right. Okay. I suppose we could put a multicolor image there.
Yeah. Yeah. Exactly. Yeah.
That's for R&D if you're listening.
Yeah. I cover them because I don't, because I find when I'm teaching people about this, they're so used to this, they look at this first and then they're biased.
Yeah, absolutely. Yeah.
I mean, often, if you're going to look at one thing, this will often get you in the right direction, but not always. But why do that when you can see the image?
Yeah.
I won't go into this slide. You can actually see this. You can go to this publication down here. But this is meant to poke fun at the way we do things.
Mm-hmm.
If this was a tumor, you wouldn't turn it into a pie chart. You'd look at it and measure, and that's what we should be doing with the OCT also.
Yeah, I've seen you. That's a really good analogy. That actually, when you're looking for very small changes, you don't measure the whole brain to see if it's thick or thin, do you?
Right.
Yeah. Yeah. And then this is a quite a controversial question. I'm going to fire it at you anyway. So we're living in this time now. Certainly, I see it everywhere I go in the UK. I'm sure it's exactly the same in the US and all around the world, where we're facing this huge new backlog due to COVID. Do you, in your opinion, think that for virtual clinics, a Hood report with a good quality OCT is enough, or do you think you're always still going to need that visual field test as well?
I think for certain kinds of screening, the answer is no. You don't need a visual field. Right. I mean, what we're telling practitioners for example, is if your workflow allows you to do it, you do an OCT first, and then you decide whether you want a 24-2 or 10-2, first of all, right?
Okay.
But for this is one of the things we're testing. But for screening purposes, the OCT will do our preliminary data. We're actually working on this very problem. Is that the OCT will do very well, right? Now, remember I said structure and function go together. Not in every eye. There are some eyes where you'll see damage first on the OCT and then on the visual field, but there are just as many eyes where you'll see it first on the visual field and then the OCT. So structure and function go together, but if you wanted the perfect world, you're going to have some early glaucoma where some individuals will show up better on visual fields and some will show up better on OCT. So you're going to have to realize that you're going to have a few false negatives if you're dependent on either one or the other.
Yes.
But the simple answer is a simple answer. We can drastically, that speaks to the times, we can drastically reduce the number of visual fields we're doing.
Yeah, that makes sense. That's a good answer. Okay, Dom. Well, thank you very much from the UK to Long Island. Have a pleasant day. And yeah, we'll hope to see you soon.
Okay, folks, thank you very much.
Okay, thanks. Bye.
See you later.